In the case where lambda squared minus omega squared is negative, your roots were minus lambda plus or minus the square root of lambda squared minus omega squared. Now, since this is now negative, we could rewrite this as negative lambda plus or minus I square root of omega squared minus lambda squared. I switched the order because I pulled out a negative, pulled it outside as the imaginary unit. Right? So then that means I can immediately write down my solution in terms of this being my alpha and this being my beta and an alpha plus or minus beta I. Right? Remember, that's where the sines and cosines come into play. So you've got a C1 e to the negative lambda t cosine square root of omega squared minus lambda squared plus C2 e to the minus lambda t. There's a t inside here, sorry. Sine square root omega squared minus lambda squared.
Why did you write the proportionality over lambda, or the negative lambda?
Which part?
On the top, you put proportionality, or alpha. Oh, did you change that value to alpha?
So remember, whenever you have a plus or minus, or alpha plus or minus beta I, it's e to the alpha t cosine of beta t and e to the alpha t sine of beta t. Those are your...
You were just doing that to sub the equation.
Right. Those are your what's called the fundamental set solutions. Is that what you're talking about up here?
Yeah. Could you write this?
Oh, absolutely. Okay. And I need to, I guess, correct somewhat of a misstatement. When I said earlier that it doesn't return to the equilibrium, that's not entirely the case. With friction, you always return to the equilibrium, but with an overdamped or critically damped case, you don't oscillate at all. You go whatever direction you first send it off into, and then it approaches it immediately. See how this, all of these, even if they go up once, they come right back down. In this case, if you look at the components of this solution, you have this e to the minus lambda t in there. And so as t goes to infinity, those are both going to 0, right? Because of the exponential to a negative exponent going to 0. Whereas these down here force you to bounce back and forth along the way, but eventually you're still going to 0. And the magnitude of your lambda determines really how fast you do that. So what you're looking at is something that, you know, starts off and then oscillates back down to 0. Okay? So that's an underdamped picture. And so all you're going to be doing in your homework is plugging in some specific numbers in for beta, lambda, or beta and omega, beta and k and m, and you use those to find your lambda and your omega. Okay? I'll tell you what, let's do. Let's just do one problem, and I'm actually going to go steal it from your homework right now so that you've got one that you can check off your list, although the numbers might be slightly different. Let's just walk through one of these free undamped problems. I'm going to go to WebAssign. Maybe. There we go.
Did you watch Villanova in North Carolina last night? That was crazy.
I watched the shot.
The last 5 minutes.
And the Rangers won.
Yes, I saw that. That I saw. That was the high point of my day.
Yeah, me too. They played. They didn't hit very well. They had a blue bird.
Oh, what am I doing? How do I go and view? I need a preview. View. Nope, not that one. This one.
It's hard. It's not hard.
Don't give me the answers cheater. All right, there we go. Okay, let's do number 4. A mass weighing 4 pounds is attached to a spring whose constant is 2 pounds per foot. I will go ahead and broadcast so you can see it up close on your screen. All right, 2 pounds per foot. The mass has a weight of 4 pounds. The medium that we're bouncing back and forth in provides a damping force, that's your friction or your air resistance, that's numerically equal to instantaneous velocity. So what does that tell me that beta is going to be? Your force for your friction or damping is numerically equal to instantaneous velocity.
1.
It's 1. If you go back and look at the derivation of the original model equation, this right here, notice your friction or your damping force is a proportional constant times your velocity. So we're saying it's exactly the same as your velocity, then beta is going to be equal to 1. K, they tell us outright, is 2. We're going to need to find the mass using the fact that it is 4 pounds. The initial mass is released from a point 1 foot above the equilibrium position with a downward velocity of 16 feet per second. Determine the time at which the mass passes through the equilibrium position. We're going to use G as 32 feet. The only thing we need G for, by the way, is to find the mass. Okay? So I'm going to, I think I've got a little tool here to chop this right here.
Just write these whole thing
There it is. For my notes, at least. So, on this example, let me switch to blue. All right, so our weight equals 4 pounds, which means the mass is 4 divided by 32, right? Because mg is equal to your weight, g being 32 feet per second squared. So you take 4 over 32, or 1/8 slugs. When your weight is in pounds and you're dividing by feet per second squared, you get slugs. Okay, we know beta is 1, K is 2. So I'm just going to go straight to my answers that I've got derived already, which are in terms of omega and lambda. So remember, lambda is beta over 2 times your mass. So 1 over 2 times 1/8. Your K is given, so your omega squared is K over M. 2 over 1/8, or 16, which means omega is also 4. Now I could plug those back into my problem, the x double prime plus 2 lambda x prime plus omega squared equals 0, and solve, but I'm actually just going to use my cases that I have already derived in my notes, right? Remember, the case is determined by what is lambda squared minus omega squared. Which would be 16 minus 16, which is 0. I'm going to scroll up for just a second. I'll come right back down. But just to remember what we're going through, when you have this problem right here, then your solution is dependent on these roots, which then you can check your case whether or not you're two real distinct roots, a single root with multiplicity, or a complex root and its conjugate. In our case, we're in case 2, so our solution looks like this. Right? So y, or x in this case, of t would be c1 e to the negative lambda, so minus 4t, plus c2t e to the negative 4t. Case 2, which implies y, or x equals c1 e to the negative lambda t plus c2t e to the negative lambda t. To get the actual solution, then we got to use our initial conditions. What are the initial conditions? What is x at 0? Well, you go back to the problem, it is released. So what is x of 0 then equal to, based on that? And don't say 1, because that's actually wrong. You're close, though.
-1?
It's -1, because down is positive for the spring, right? And up was negative. At least the way that we derived it, and I'm assuming the way he derived it. I'm pretty sure that's the way he did it in the book. I'll double check. I don't even want to give you wrong information, so I gotta look back in the book. The picture that he drew. Yes. It's on page 193 if you look it up in your ebook. I know you use your ebook all the time. All right. And then what's the initial velocity? Positive or negative 16?
Positive.
Positive. Exactly. And so now we just do x of 0 equals -1 means,
Could you go back up a little bit?
sure. You plug in 0, you get C1, because 0 here cancels out the second term. So all you've got is C1 times 1, so C1 then equals the -1. And now x prime is -4 C1 e to the -4t. And now I've got to do a product rule, so plus C2 e to the -4t minus 4c2t e to the -4t. So plug in C1 is -1, and also do x prime at 0. So that gives me a +4 from here. -4 times -1 times 1. Plus C2 minus 0 equals 16, so C2 is 12. So my final answer is negative e to the -4t plus 12t e to the -4t. Then you got to use that to answer the questions they provided. But where did I lose you?
On the x prime t, should that be x prime 0? Or,
Well, I took the derivative first,
yeah.
right?
Oh, okay, I got you, I got you.
And then I'm going to plug in 0. I usually insert that step whenever I'm working these problems so that I don't take the derivative and plug in 0 at the same time. So how would we determine the time at which the mass passes through the equilibrium? I mean, that's the question that the problem is asking first.
So we set it equal to 0?
Set it equal to 0. In this case, they both have an e to the minus 4t in common, so that's how you're going to solve that, is by factoring. So set x of t equal to 0. Minus e to the minus 4t plus 12t e to the minus 4t is equal to 0. E to the minus 4t you factor out, which will never be 0, and you get negative 1 plus 12t. So it's when negative 1 plus 12t is equal to 0, where t is 1/12 of a second.
It looked a lot more intimidating than that.
You just got to remember where to put all the numbers, and it really is very simple. I'm going to scoot back for just a second. I'll be right back to this page. I want to look at the question. Find the time after the mass passes through the equilibrium that the mass attains its extreme displacement from the equilibrium position. It's a fancy way of asking another fairly simple calculus question. Would you say? It's when the velocity is equal to 0. So after 1/12 of a second, it passes through. It's going to come back up. So, I mean, the picture that you should have in your mind of what this thing is doing is that it started at -1, right? And it had an upward velocity. It was thrown upwards. Okay? At 1/12 of a second, it crosses here, and then it's going to start to come back down.
How are we?
And in fact, the only reason we know it doesn't cross again is that there's no other 0 to this equation. It never crosses equilibrium again, right? And we know that in the long term, if we look at this right here, as t goes to infinity, that's going to 0. So we know it went up, it crossed the equilibrium, and it's going to come back down, and it's going to approach 0 after that. The question is, where does it hit that maximum? And because it's a nice continuous function, it hits maximums where its first derivative is 0 at a horizontal tangent. Okay? So when does the mass reach maximum displacement after t equals 1/12? The answer is when x prime of t is equal to 0. Okay, so find x prime of t. We kind of have it, but we have it with c's in there. I'm just going to take it again. You get a, what is it, 4? E to the negative 4t plus 12e to the minus 4t minus 48te to the negative 4t, or 16e to the minus 4t minus 48te to the minus 4t. Is that right? Is that the right derivative? Right, take the derivative of this term and then use the product rule on the second term. And what we're going to do with this? Well, set it equal to 0. So pull out the e to the minus 4t again. 16 minus 48t equals 0. And technically, I should set both of these equal to 0, but the reason I'm skipping setting this first term equal, or first factor equal to 0, is because it's never 0. E to the minus 4t is a radioactive decay looking curve, right? It's the exponential downward, but it's approaching 0, but it never actually crosses 0. So I set these equal to 0. That can't be 0, so 16 minus 48t equals 0. You have a question, Dylan?
On the x prime and t.
I'm taking the derivative of this, right? The solution we came up with,
Gotcha. Okay.
right? That's the solution equation. And then I use that to answer the first question, which was, when does it cross 0? When does it cross the equilibrium? Second question is, when does it reach maximum displacement? That's when, as far as it goes, and then before it starts coming back, that's going to be where the derivative is 0, where it's horizontal. Same way you find maximums in Cal 1. Set the first derivative equal to 0. So t is 1/3 of a second. Okay? And I don't remember what the last question was, so give me just a second to sneak a peek. What is the position of the mass at that instant? So how do you answer that?
Go back to your position.
Plug up into the solution equation. X of 1/3 is negative e to the negative 4 times 1/3 plus 12 times 1/3 e to the negative 4 times 1/3. Plug that into your calculator, get a number, and that'll tell you how many feet away from equilibrium you are. Which I'm not going to bother to do, because that's a mere number. Any other questions about this? The last thing, I guess I should go ahead and mention this. At the end of this section, he also has a third scenario, Roman numeral 3. So the first Roman numeral was free, undamped motion, which meant no friction, no damping, right? Those are two different things. That's the same thing. No, nothing slowing this thing down based on how fast it gets. So no damping. There's just the spring and there's just gravity, and that's it. Okay? You displace it, you let it go, it'll move forever in an oscillating form. You add damping, it will either make one jump back and then settle down to equilibrium, or it'll just go straight to the equilibrium. Or if the damping is low enough, it'll oscillate, but eventually go to equilibrium. Okay? The three different cases for free damped motion. Now the last one is, you can have damped or undamped, but you add or I guess you take away the free thing. What's free? Free means nothing is happening external to this system. There's no other forces involved. Okay? So if you add another force, you have what's called forced motion. Which could be damped or undamped, by the way. But the only thing different from Roman numeral 1 and 2 is that instead of it being homogeneous, there's now a function on the right-hand side. X double prime, right, a mass plus beta x prime plus mx is now some function f of t, okay? A forcing function. That forcing function could be me pushing on it periodically. It could be the some kind of oscillator attached to it that forces it to align with itself. So something like a crank or another spring attached to it, or some kind of motion forcing system attached to it. I mean, in my mind, the simplest picture I can come up with, besides me just hitting the mass periodically, is that there is maybe some kind of attachment here where we've got a gear attached and this thing is going around in a circle. Okay? So you are able to move the spring along there, but as you start this crank and it's turning around, there's an external force acting on that spring itself. Okay. So the only thing different that you've got to do now is we might still write this as x double prime plus 2 lambda x prime plus omega squared x equals some g of t. Notice in this case the only difference now is g of t is now f of t divided by the mass. But let's say we consider solving this. In practice, the techniques that we have right now are either method of undetermined coefficients or variation of parameters based on what's on the right-hand side. So it's the same type of problem we've solved before. So for the homogeneous case, y sub h, use the same three cases as above. Then find y sub p. Note, what's interesting about the solution is that as t goes to infinity, the solution y, which is the y sub h plus y sub p, will approach y sub p. It'll always end up in the long term matching the long term behavior of y sub p. It has an asymptotic relationship to the particular function, and the particular function is determined by the right hand side, the forcing equation. And that's actually pretty clear since y sub h goes to 0 in every case, right? In both free damped and free undamped motion, eventually the homogeneous solution, well, I should say, I'm being careless, but when beta is greater than 0, I want to make sure I say that. When there's damping, you're going to approach your particular solution. I'm not going to do an example. I'll pull one up here in just a second when you have a chance to finish writing down my note. But I give you, I think, one problem in your homework where you've got a function on the right-hand side that you have to solve. So it's still the same technique from either variation of parameters or method of undetermined coefficients to find the solution. You just got to make sure you get the beta and the k in the right place. I think I screwed up. This should not be an m here. That was a k. Fix that in your notes if you wrote m there. My apologies. Right here. I wrote m again next to x, but that k, that's k, which is your spring constant. It wouldn't be the mass again. Okay, so in your homework, I think the one problem, I'm going to scroll down here, I give you this one right here. And actually 5 and 6 both are the same kind of problem where you've got a forcing equation on the right-hand side. So let me at least point out one thing on here. And that's when you're given this, that's assuming your equation is in the form mx double prime plus beta x prime plus kx equals f of t. So on this problem number 5, we'll write as a homework hint on the other one, first divide through by m. All the way across. Okay. So, let me get rid of this. Example, homework 5. If given a forcing function f of t, rewrite as x double prime plus 2 lambda x prime plus omega squared x equals g of t, where g of t is f of t divided by m. And solve this. I mean, that's not a hard and fast rule that says if you don't do that, you're going to get it wrong. You can solve the original equation up here, but then you don't have the advantage of reusing everything we did in Roman numeral 1 and Roman numeral 2. And just again, one more time, lambda is beta over 2m, and omega is the square root of k over m. I think what you'll get a feel for, I mean, one of the things that you're learning about all of this modeling in Chapter 5 is the use of these parameters that you can fiddle with to see the impact that it has on the solution. The lambda and the omega, for example. When you do your group project, you're going to find in every case that they give you a model to help set up. You're going to need to explain where the model equation comes from, but then there are going to be parameters in the model that are based on physical parameters in the actual physical phenomena. Like if you're talking about bungee cord, you're going to be talking about the stiffness of the bungee cord. If you're talking about the water clock, it has to do with the actual dimensions of things. So you're going to be basically exploring the impact of modifying those parameters and what impact it has on the solution, the shapes of the solution curves, which is exactly what we've done here. So it's one of the reasons why I decided to go ahead and stick this in in chapter 5. Kind of in the middle of where we're talking about systems, we just kind of took a little bit of a break, went back to solving higher order linear differential equations. Now we're going to go back to systems now that I've wrapped this up. Okay, so this homework is due Thursday. I'm now ready to take the last half of class today and get us started in chapter 8. I'm going to skip over chapter 6, which is a lot of stuff on series solutions, power series. I'm going to skip over Laplace transforms, and I've decided to go with systems as our crowning achievement for undergraduate differential equations for you. Okay. Actually, not the very last thing I will do is still do numerical analysis stuff. I got to throw that in at the end. If I don't do that, then I'm not true to who I am as a numerical analyst. All right, so I'm going to stop this.